Good morning, everybody. Welcome. So please take your seats, quiet down, and be ready to learn some fun stuff. My name is Andrew Beltaos. I am a lecturer in the math faculty. And I don't know if you know, but math, their color is pink and the tie is the pink tie. So I've got this. This is my true self. But at the same time, I do teach engineering quite a bit. So this fall, I'm going to be teaching Math 116, which many of you will be taking. And then Math 118 after that, Calculus 1 and 2 for many of you. So the idea is for me to give you a sample lecture of a math class, a calculus class. And what we're doing today is not exactly calculus per se, but it is something that is covered in the Math 116 course and the Math 117 course. So it's a topic that right now, if you learn it and do well today, then you have a little bit of a head start already for fall. So I think I'll just get to it. I'm going to just treat this like a normal lecture after I'm finished this little intro that I'm giving you right now. So if everyone's ready, I will get started. Okay. So today's topic is the Heaviside function. Has anyone heard of the Heaviside function? All the upper year engineering students have heard of it. Yes, and they are good at it. And later they'll be running the tutorials and helping you with it if you have any problems with it. So to start off, I'm going to introduce to you what this function is. And it's called the Heaviside function. The Heaviside function, sometimes called the Heaviside step function or the unit step function. The Heaviside function is defined as h of x equals, it's a piecewise function. So I know that you all remember piecewise functions. You know, this function is equal to this expression for some x values and some other expression for these other x values. This is a piecewise function that's very simple. So 0 if x is less than 0, and 1 if x is greater than 0. That's how this function is defined. So for the rest of today's lecture, and when I use the capital letter h, I'm talking about this particular function. And this particular function h, you can plug stuff into it. What it is, it's basically an on-off kind of function. If you input a negative number into it, so if x is negative, then h of x gives you 0 as the output. If you input a positive number, if x is greater than 0, then the output is 1. So it takes an input and it looks at it and it goes, is this positive or negative? And then once it determines the answer, it spits out the result, which is 1 if the input is positive and 0 if the input is negative. So it's a bit of a sign, as in plus or minus signs, detector. Okay? So it spits out 0 for negative numbers and 1 for positive numbers. And there is this sort of idea of, well, what happens exactly at 0? I don't know if any of you was wondering about that, but it's actually sort of up for debate. So 8 out of 10 mathematicians do not all agree on exactly how to define this function at 0. Some people define it as 1/2 at 0 because it's sort of the in-between, between 0 and 1. Some people define it as just sort of an inclusion here. They just say greater than or equal to. I'm going to erase this, but just as an example. Or they put the less than or equal to there. Some people, which is what I will do for today, basically to keep things simple, just leave it undefined at 0. So don't worry about it. The idea with this function, the inspiration behind it, is something that will just make something turn on, basically. So prior to 0, this function is just 0. So let's graph it, which is really easy to do. So the graph looks something like this. Here's the x-axis, here's the y-axis, here's 1, and you've got, now it's hard to draw the 0 function because it coincides exactly with the x-axis, but hopefully you can see that squiggly line. That's just meant to be the graph going up to 0, and then after that, it hits 1. So basically something was off, and then suddenly light turns on, and it's on. And this is, again, this discussion of, well, what happens exactly at 0? In some cases, we just say, or at least for today, we say, who cares? When I flick a light switch, I know that before I flicked the light switch, it was off, and after I turned it on, the light was on. And what was happening at the exact moment when I actually touched the switch doesn't really matter. We're trying to model a behavior of here's what was happening before, here's what was happening after. So for our purposes, this is the graph of y equals h of x. Okay? So, does everyone understand what h of x is defined as? Yes, question? This is y equals 0 for x negative, and then y equals 1 for x positive. I've drawn it squiggly only so you can see it, not because it literally squiggles, okay? So if you want, I could just make it a thicker line, and then make this one thicker, and then that's the graph of the function. Maybe that would have been better, okay? I didn't mean to confuse you with the squiggles. Okay, so everyone knows what h is, and so if I say, what is h of 5, you would all say 1, because I think I heard everybody say because 5 is positive, right? So you take a number, look at if it's positive, spit out 1. So h of negative 807 is 0. If I plug in a negative number, the output is 0. So it's as simple as that. It is literally as simple as that. So what is the graph? So let's graph this other function, f of x equals sine of x multiplied by h of x minus pi. Suddenly it's a little bit more complicated. It looks all complicated, but it's not complicated at all. What you have to remember is that h of anything, as you all very well know, is either 0 or 1 depending on what the input is. So x minus pi is the input. So depending on whether x minus pi is positive or negative, you're either going to get a 1 or a 0 replacing this capital H of stuff, right? So we've got a sine function multiplied by a 0 that later turns into a 1, okay? And that's the way we look at it. So let's write this. Let's graph this. But first, let's write f in piecewise form. In piecewise form. So f of x equals, there's two pieces to this because there's a single h function. And just the way I've defined capital H of x over there, something if x is less than 0, something else if x is greater than 0, over here, it's something if x minus pi is less than 0, and something else if x minus pi is greater than 0. Is that clear enough to everybody? So are you comfortable with me saying something if, I'll fill this in a moment, if x is less than pi, and then something else if x is greater than pi? You see why that's the two cases in this piecewise function? Is this unclear for anyone? Don't be shy. Just raise your hand and ask for clarification. Even if it's just, well, why is it that? Why isn't it not just x less than 0 or x greater than 0? My goal is just to make sure you all understand this, right? So if you're having any confusion, just let me know. What I'm really doing is x minus pi is negative. Oh, I didn't see the hand. Yes? Okay, well, because, let's go over here, h of x is 0 if x is negative, yes? So h of thing is 0 if thing is negative. And this particular thing is x minus pi. Okay, so if x minus pi is negative, that's another way of saying this. If you can see it, x less than pi is the same as saying x minus pi is negative. Does that make sense to everybody? Okay, great. And again, good questions are good. Don't be shy, everybody, if you have questions. So if x is less than pi, then what do I put here? 0, right? H of x minus pi is 0. I mean, it's 0 times sine x, but you don't need to bother writing sine x. 0 times anything is still 0. And then what do I put here? Sine x. Everybody within a certain percentage of error, I don't know if everyone spoke, but it sounded like all of you saying sine x. So yeah, all of you approximately are right. It's just sine x because it's sine x times 0, and then later it's sine x times 1. It's this. So it's sine x, and so graphing it is suddenly really easy, right? Graphing it. So we know what the sine function looks like. And I'm going to do something kind of weird here. What I'm going to do is plot the sine function normally and then erase part of it. So don't write everything I write just yet. You know how to graph the sine function. Pi, 2 pi, negative 2 pi, and so on. 1, negative 1. These are the important features of a simple sine function. So you graph it, and it goes up and then comes down. So forgive me if my drawing skills are not as good as yours, because they're definitely not. But the function sine x, again, don't copy this down just yet. The sine x function looks something like that, but we're multiplying it by a 0 prior to x equals pi. So actually, we have to erase everything to the left. I drew it all because I wanted you to see this is what's being multiplied by 0 here and then 1 there. So it's almost like the Heaviside function is this invisibility cloak that just sort of covers everything before a certain point, if that makes any sense. So actually, we don't have any of this. It's just simply not there. So what this graph really looks like, and I put a circle meaning I'm not including the endpoint because of the nature of this Heaviside function. So it's a sine function to the right of pi and 0 to the left of pi. And I'll do that thick line instead of the squiggle because I've learned something about squiggles. So there's the actual function, and then over here, just 0 to the left. Okay? Yep. Why what's pi? Okay, sure. So back to this. I'm trying to think of the best way of saying this. Okay, so just over here, h of x minus pi, just the h part, is equal to 0 or 1 depending on the argument of the function. You're inputting x minus pi. So there it is in black and green. That's the intermediate step that I didn't really write. So 0 if that's less than 0, and 1 if that is greater than 0. And then I translated this, because it looks too complicated, into x less than pi. Okay? Yep. Yeah, will we be working in radians? Yeah, we're just working in radians. Let's just keep it at radians. All math, at least in the courses I teach, Calculus 1 and 2 and stuff like that, we're always working in radians. Yeah. So yeah, you could think of that as 90, 180, 360, all that kind of stuff, but let's just stick with radians. Yep. Sine function starts by going up and then coming down after. So, okay, you said since it's shifted, right? Now, those who have been in my class before, and some of the TAs have been in my class, they know that I have this cause that I like to put forth, which is avoid the word it when you're talking math. You said it's shifted. Sure, it is shifted, but what is it in that sentence you said? Only the h is shifted, right? So you've got a 0, 1 shifted multiplied by a regular proper sine function. So the sine function is just there, and that's what I was saying. The h is the shifted, and that's like an invisibility cloak that just makes this part disappear, but it's still just a normal sine function. Sine x multiplied by 1 is certainly just sine x. Make sense? If I had sine of x minus pi times h of x minus pi, then that would be starting everything shifted over. Yes?
So the argument just determines where the graph is on and off?
Yes, exactly. The argument just determines where the graph is on and off, basically. That's a nice way of summarizing it. Okay? And that's a way of summarizing the last 10 minutes. So I could have said it quickly, but it's new to you. I want to make sure that everybody understands this concept without just saying, here it is, deal with it, right? Okay, so we're over here. So now let's just get a little bit more complicated. So one of the things I want you to be able to do is be able to translate a quote-unquote complicated expression in terms of sine functions into a simplified piecewise form. We already did it with this example, but let's make your life a little bit more difficult. So I'll do an example. Express f of x equals, and I've got an example written down. It's just nice if I have the same example that I wrote down, so excuse me while I get my notes here. So 2 times h of 5 minus x minus bracket x minus 3 times h of x minus 2. Express this function as a simplified piecewise function. And this question is actually super easy once you get used to it. But until you're used to it, it's a little bit weird. So don't feel bad if you do feel that it's weird. And do feel good if you're like, yeah, I totally get this. Okay, honestly. So here's the function f of x, 2 times h of 5 minus x minus 3 times h of x minus 2. And don't be distracted by the way the notation looks, like I've got to bracket this and then a capital H and then another bracket. H of x minus 2 is its own thing, right? You understand function notation. So h of stuff, that's this. And then over here, the x minus 3 is literally multiplying by the number x minus 3, okay? So just make sure you're understanding the order of the way stuff is written. Okay, so how do we express that as a simplified piecewise function? I have a suggestion over here, yeah?
The first term, h of x would be 1 if x is less than 4.
4? 5, 5. Yeah, so for the first term, h of x, h of 5 minus x, will be 1 if x is less than 5, and then 0 if x is greater than 5. So I purposely threw in a curveball, right? This is 5 minus x and not x minus 5, so you have to think if x is some really large negative number, or any number less than 5, like 4 or 3 or something, 5 minus x is positive, so h of that will be positive 1. Yes, and then if x is greater than 5, 5 minus 6 is suddenly negative, so h of a negative number will be 0. So one thing you've pointed out, rather than just answering the whole question all at once, you've pointed out a single piece, which is that this h changes at x equals 5. And similarly, this h changes at x equals 2. So already, before I do anything else, I'm going to answer the question by saying f of x equals a piecewise function that changes at 2 and 5. So I just sort of chronologically write the cases. I need spaces for 3 different cases here, right? So the first case, in fact, I think I need a little bit more space because I'm going to write a lot. So I'm not changing anything. I'm just shifting it a little bit to the left here. Okay, so it's something if x is less than 2, something different if x is between 2 and 5, and yet another thing if x is greater than 5. That much we can do without thinking too deeply about what the details end up giving as the final result, right? And this is a suggestion for you, is about how to organize your approach in mathematical thinking or logical thinking in general. Take things one step at a time. The first thing to realize is that there's changes happening at 2 and 5, so organize your real line like that. After that, we figure out the details. And I'm going to take that thinking to the extreme and say, you know what? When x is less than 2, this is 2 times h of 5 minus x minus 3 times h of x minus 2. That's not wrong. I just didn't do anything. I'm not done. That's why. I'm going to interpret that. So I'm going to write the same thing every time. I'm basically figuratively, literally figuratively, copying and pasting the same function every time, because it is the same expression every time. But after that, what I'm going to do is interpret and say, well, what are these h's? Let's replace them with what they really are as I get to the different regions, okay? So this is sort of silly to do it like this, but I feel it's really helpful to do this way, because after that, you can simplify your expressions. So there's something if x is less than 2, something else if x is between 2 and 5, and something else if x is greater than 5. So technically I've answered this correctly, except the question said simplified. So we have to simplify first. So the next step is to look at those h's, h of 5 minus x and h of x minus 2, and replace them with what they really are. And again, it looks complicated, but don't be confused. H of anything is always just a 0 or a 1, depending on where you are on the real line. So it's not nearly as complicated as it looks at this point. And I've got red chalk and green chalk, and I apologize to anyone who's colorblind. But even if you are, I'm going to write the correct things So you'll still be able to see what I'm writing, but for those of you who do see in color, green will be 1 and red will be 0, so it's like on-off kind of thing. So first of all, if x is less than 2, let's take this one step at a time. Here's the easy one. What's h of x minus 2 if x is less than 2? 0, because if you plug in a number less than 2 and then you subtract 2, you get to the negative zone, right? So h of a negative number is 0. So I'm going to circle this in red and then say 0 in that region. And why don't we just remain on this track of thinking with the h of x minus 2? What about if x is greater than 2 and less than 5? Is h of x minus 2 0 or 1? 1, because x is greater than 2. The fact that it's less than 5 is kind of immaterial, but x is greater than 2, so bigger number than 2 minus 2 is positive. H of a positive number is 1. So this piece gets replaced with a 1. And if x is even larger, greater than 5, it's still greater than 2. So this h of x minus 2 is still 1. So it's kind of like this h of x minus 2 was a surprise party waiting with an x minus 3 attached to it until 2 o'clock, and then here I am, and then it just stayed there for the rest of eternity, right? Okay, and now this other piece, this is back to your observation. You said h of 5 minus x is 1 if x is less than 5. In particular, why don't we do that in a really, well, we'll take that fact. We talked about it, right? If x is less than 5, you subtract 5 minus something small, positive. So h of a positive thing is, h of a positive number is 1. So this is 1. X is still less than 5, so h of 5 minus x is still 1. And finally, x greater than 5, this h of 5 minus x is like, finally I can take a break, right? H of 5 minus x, subtract a number bigger than 5, you're negative. So h of a negative number is 0, so I got to switch my chalk colors. 0. Now, it's not nearly as daunting. I've replaced all the h's, or I've interpreted all the h's as 0s or 1s accordingly. So now I just write another step, which is 2 times 1 minus 0. Okay, the first piece is just 2. Not a big deal. The second piece, they're both 1s there. So I'm going to write it in small steps, even though you are probably very tempted to simplify it all at once and write negative x plus 5. Yeah, that's fine with me, but I want to take small steps to make sure that everything's super clear. And then 0 there, 1 here, so negative x plus 3, I could write it. Let me know if I've made a mistake. I mean, I'm just thinking about this just as you are, so my notes are way over there. I can't check them. I'm too lazy to walk over there. Okay, so I think that's right. So finally, the very last simplified version, I mean, you know what it is. 2 negative x, don't tell me, 2 plus 3 is 5. Okay, there we go, negative x plus 5, and then negative x plus 3. And then I put in those regions one more time. X less than 2, if 2 less than x less than 5, and then if x is greater than 5. Okay, and there it is. There's the simplified piecewise version of the original function, which was this. It's all on the same set of boards. So that's the original function, and this is translating it into piecewise form. And that's how you can interpret it. If you had to graph it, for example, say I said graph f of x equals this. It would be hard to organize just like, oh, clearly this graph looks like this. But if you do these steps and then you turn it into this piecewise function, now it is pretty clear. You know how to graph constant linear functions and stuff like that. So it's all good, right? Yes? Oh, you mean the 2, 5 thing? I don't care which. This is just a matter of taste, basically. Interval notation? Yeah. Interval notation or inequalities, I don't really care which. I'm saying the same thing in different ways. So it's tomato, tomato, etc. Potato, potato, either, either. Okay. So So any questions about that? I have to stay away from the speaker because it gets feedback. Okay, so you've seen now, you know how to do one of two things that I wanted to tell you how to do. The first thing was take a Heaviside expression and translate it into a piecewise expression. Now I want to teach you how to take a piecewise expression and then go backwards and encode that back into a Heaviside expression. So the next example is going to be, here's a piecewise function, and write it in terms of Heaviside functions. And those are basically the two main things that are my goal for today's short lecture. Okay, so here's another example. Write g of x equals 2x plus 1, x plus 2, and sine x, these three pieces, for these different regions of x. So if x is less than -1, if x is between -1 and 0, and then if x is greater than 0. Okay, so it's a piecewise function. I'm using the letter g to be a different function than the previous example. That was called f. So what am I saying? Write g of x, and if I just put a period here, it would be a really easy example. Okay, I'll write it. But write this in terms of Heaviside functions. And I say Heaviside functions plural because there's going to be more than one. Maybe you're already seeing that if you've already started thinking about how you would approach this problem. I've got a transition at -1 and then another transition at 0. So there's going to be an h of different things, right? So what are my h of stuff that's going to be in there? Maybe someone in the back, just because I know the people who sit in the back tend to sit in the back because they don't want to answer questions, so I'm going to make you. So does anyone in the back have an idea of a h of something that I could write as part of the answer, even if you don't know the whole answer? You were close enough to the back, yes? The last piece is going to involve a sine x times h of x, or something like that, for sure. H of x particularly because there's a transition at 0. So if you're transitioning at 0, that's just h of x, the simplest version that I started with. And so now someone else, what about to capture that -1 transition, h of, Blue Jay's hat? H of x plus 1, right? I mean, I think of it as h of x minus wherever the transition is, and x minus -1 is x plus 1. So you've simplified it already. There's going to be an h of x plus 1 to capture this transition. There's going to be an h of x to capture that transition. That's the way that I look at it. And you know what? There are many ways of looking at it. I'll tell you right now, if you had other ideas, they might be right, even if they're different from mine. And I'll talk about that a little bit more if I have time at the end. Okay, so my suggestion is to start sort of left to right on the real axis. Or if you're thinking time, start from the beginning of the universe and then go into the future later, if the x variable is time. So let's think of that just intuitively for a second. Before -1, so since the beginning of time, there was 2x plus 1. So here's what I'm going to do. I'm going to say 2x plus 1, and then after that, I'm going to put plus something that I don't know what it will be yet, times h of x plus 1. And I'm going to put another piece, and just bear with me for a moment. If you're like, where are you getting this from? Give me a moment, and then I'll explain it. If the structure of my answer is like that, I know that I'm on the right track, because h of x plus 1 will be 0 before -1, and h of x will also be 0 before -1. So whatever goes in here, it doesn't really matter yet if I'm just considering x less than -1. 2x plus 1 is what happens first. And then after that, at -1, something gets turned on. So we're going to have to figure out what to put in here, what arrives at -1 to put in here. But just to start thinking from left to right, prior to -1, it's currently correct, right? Our answer is currently correct. So now we just have to think, what could we put in these brackets here to capture the changeovers? And I'll tell you, conceptually, it takes a bit to wrap your brain around it, but there's a trick that makes it super easy to just do. And in some ways, I don't want to encourage you to just learn a trick and just do that, because it's way better to understand stuff. But in the end, it ends up being so easy that you just remember what to do. Did you have a question or a suggestion? Yeah. You know what to put here? A constant variable or something? And then figure out what it has to be. Basically, you know, what you're saying is, it sounds very much correct, but it sounds like you've already done more than you have to. You talked about subtracting one and the other, and that's basically it. So you're saying make it a variable and then say it has to be the subtraction of x plus 2 minus 2x plus 1. I think that's what you said, right? And that's really the whole key. And let's take the variable out of the picture, because I think you don't even need it. At x equals negative 1, the function switches to x plus 2, right? So in order to make this transition capture an x plus 2 suddenly, all we have to do is bring in an x plus 2, but then get rid of what was there before. So some of you will just know the answer, but before that, I'm going to write it in sort of a long-winded way, new thing minus old thing. I multiply by the new minus the old, right? And of course, you could simplify that, and maybe you didn't even think of it in this way, and you just thought, well, I would have to subtract x to turn this 2x into a regular x, and I would have to add 1 to turn this 1 into a 2, so the answer was going to be negative x plus 1. You might have been thinking that, but what you're really doing when you're doing that is you're saying, I'm going to throw out the old thing because it's gone, and then bring in the new thing because it's here now. And that's probably a better, more generalizable way of approaching it. Because what if they're not the same kinds of polynomials, and then you can't just think of each term separately. You just say, look, a new thing arrived and an old thing went away, so I'm literally going to subtract the old thing and add the new thing, and that's really what's happening at x equals negative 1. It captures like the tag team swapping out and back in, right? 2x plus 1 went home and x plus 2 showed up. So subtracting it is making it go home. Why? I mean, it's not all like fuzzy with words, because when x is greater than negative 1, this whole thing is simply the number 1. So this whole h of x plus 1 is suddenly the number 1, so I have 2x plus 1 plus this new thing minus 2x plus 1. The 2x plus 1's cancel, and I just have the x plus 2 staying there. Makes sense? Now, the second transition, this is what I was telling you. There's a simple trick, which is basically new minus old. If that's not clear, I will just make a little comment there with the red. So this is new minus old. That's really what you put in there to capture those transitions. So in that spirit, what do I put multiplying the h of x, okay? What's the new? Sine x arrived. And what's the old? So who votes 2x plus 1 plus x plus 2? I'm purposely throwing out a wrong answer that no one is taking. Okay, so who votes x plus 2? I mean, in brackets. Who votes something else? Yeah? All this? All this. And the one before that. So this is what I'm trying to capture, is you don't need to worry about the one before it because it's already accommodated for. That's the weird thing about it. So after 0, let's think we're to the right of 0, because before that, this is off, so it doesn't matter, right? Before 0, this is a 0 here, so we don't care. But after 0, when x is to the right of 0, this is a 1, and so is this. So these are all there. So if I want to capture everything, I get 2x plus 1 plus x plus 2 minus 2x plus 1, which is, that stuff is gone. So I just have the x plus 2 for now. And then I say plus sine x, but I don't want to have the x plus 2 anymore. So I have to subtract what was there before and only that. Does that make sense? It's easier to go the other way. The previous example we did went the other way around, right? We went from an expression like this and we turned it into a piecewise function. That was easy because you just replaced the h's with zeros and ones as appropriate, the earlier example I did. Well, Now apply that if you want to check your work. Apply that to this, and you'll see that it works out to the right thing. We could simplify a little bit over here, so let's do that. Just to like nicely have a final answer that makes sense and is simplified. So therefore, g of x equals 2x plus 1 plus, and I'm going to put some brackets here, times h of x plus 1, and what goes in those brackets? Negative x plus 2 minus 1 plus 1. And then the last piece is plus sine x minus 2. I could write it like that, times h of x. And that will capture all the behavior. I hope I didn't make a mistake. Are there any questions or corrections? Yes? You went about it a different way, and you think your answer is also sort of right. I would not be surprised if your answer was also completely right. Go ahead. Say that one more time, that last part. You put h of x is next to it? So you didn't put h of x necessarily. You put h of negative 1 minus x maybe? Or negative x minus 1 or something like that. So yes. And so, I mean, I don't want to get into that because it takes time. And we are basically almost out of time right now. So just at the more intuitive level to explain the idea rather than every detail, this suggestion is a really good one. It's a different way of approaching it. And it's not just start with this and then add new minus old times this transition plus new minus old times that transition. The idea, which is a good one, is sort of think of it as a timed turning off instead of a timed turning on of a subtraction, right? The way I'm thinking of it is there was this subtraction that's ready to go at negative 1 and this other subtraction that's ready to go when x reaches 0. What you're thinking is, look, there's this function, and we're going to have it multiplied by 1 first and then 0 later to make it go away. And then you're approaching each piece like that. And that does work. It totally works. And again, just in the interest of time, rather than going through the entire answer like that, I just want to say, yes, that's a good idea, and you could do it like that. Some people come up with even more interesting ideas as well, other interesting ideas like multiplying two h's together. And then you sort of get, like, when these two things multiply together, if they're both 0 in that region, then everything's 0. Or if any one of them is 0, then in that region, everything's 0. But if they're both 1 for a particular region, then you get them to be 1 only then. So you can multiply Heaviside functions as well. You can be very creative. H of x is the building block of being able to write just about any piecewise function. And I say just about because technically I'm limited because I can't do anything that has inclusion on the inequalities. That's a bit of a problem with this way I've defined it. But that comes back to what I was saying at the beginning when I said here's h of x, 0 for negative, 1 for positive, and then I said what happens at 0, we don't care. Well, if we defined it differently and we allowed inclusion, then you could capture any piecewise function in terms of Heaviside functions. And that will be on your tutorial. So on your tutorial, there's questions which you're going to get. Maybe you have them already, which asks you to do questions like this one and like the other example I did. And then there's ones that go into more detail that say, what if we try to include one of the endpoints? Think about it then. So I think that we're basically done. This is the basic goal of what I wanted to show you. Are there any last questions before we say goodbye? Yes? Are you going to be able to record lectures? Yes, basically. It depends on the instructor. You should ask permission, but usually everybody says yes, especially if there's a need for it. Sometimes there's students who really need it for whatever reason or just request it. You just ask the instructor. They're okay with it. Yes? Yep. Is the purpose of lectures in the university to learn the topic, or are you just supposed to review it? It's sort of a combination of both. I mean, the schedules are jam-packed, so in one lecture, here's the topic, here's an example, okay, next topic, right? So there's not a lot of time to talk about it again and get more practice with it. So you learning it, you have to do the math yourself. But in the lecture, we do our best to convey those topics. Okay? One last question before we finish. Sorry, I couldn't hear you. Just one moment, everybody. Yes? I didn't hear again. To use a calculator? It depends on the instructor too. In my Math 116 class, no for the exams and the midterms. But it's just you get questions that don't need calculators. How much did we need a calculator here? You know, so don't worry too much about that. So yeah, one last question. Was this an example of an average, easy, or hard lecture? I guess I'll go with average. There are some easier topics, there are some harder topics. This is sort of average. Yeah. Okay? So I think it's time to go. Thank you, everybody. Have fun at the tutorial.